Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the first module of this course, that is the introduction module. And the idea behind this module is to give you a basic introduction to operating systems. So currently within this first module we are on the second topic, that is introduction to operating systems. In this topic we are trying to understand what is an operating system and what does it do, right? So basically the operating system is a special piece of software that manages the computer hardware. We know this, and what we have been doing is that we have been focusing on the individual hardware components and seeing how the operating system manages that particular piece of hardware. So in the previous few videos we have talked about the CPU and also the memory. Now in this video let's focus on the IO devices and see how the operating system manages the IO devices or the input and output devices. So let's get started. So before we talk about how the operating system manages these IO devices, let us quickly recall the role of the IO devices in the computer system. So the basic flow of computing goes something like this. We as users give our input, and that input is processed by the computer, right? And some output is produced, and that output is consumed by the user. So now if you see this flow, there must be a mechanism via which the user can give their input and consume that output. So that is where the IO devices are helpful. They help the user to interact with the system. So we have a set of input devices like the keyboard, mouse. As I am speaking, this audio device is there. The camera is recording my video. So there are a lot of input devices via which we can give the input. And then again, there are several output devices like the monitor, the speaker. So all of these are devices from which we can consume the output. So this is why we have the IO devices in the computer system. Before we start talking about how the operating system manages the IO devices, let us see how the interface of the IO device looks like from the perspective of the operating system. So here is the computer system, and as you can see, we have a set of IO devices. So let us see how these IO devices are organized. Let's take the example of the keyboard. So this is the figure which shows how the IO devices are organized. As we know, there are two parts to any IO device. First of all, there is the device itself, and then associated with the device, there is an electronic chip, that is the device controller, which is responsible for controlling the device. Now, in this case, we have the keyboard, and this is the keyboard controller. This gray region that you see, this is meant to show that this part is inside the computer system. This is internal in the computer system, and this portion is external, right? And this is the periphery of the computer system. Now there are two connections. The first connection is where the device connects with the device controller. So this is called the device port. So as you can see, there is a wire leading out from the keyboard, and this is a USB cable, and this will plug into the device port, right? This will be a USB port. So this is where the device will connect with the controller, and the other connection is internal inside the computer system. So this connection is where the device controller is connected with the bus, and as you can see, this is called the device controller interface. It has a set of registers, and the operating system communicates with the device controller via these set of registers. So the operating system can read or write these registers, give commands, check the status. So all communication between the operating system and the device controller happens via this interface. So this is how the IO devices are organized. So now that we have understood how the IO devices are organized, let's see what is the hardware interface that these devices expose to the operating system. So this is the compute stack, and as you can see, there are two layers in the hardware. The first one is the device, and then we have the device controller on top of the device. Accordingly, there are two interfaces. The first one is the device interface, and the other one is the device controller interface. So as you can see, the operating system never communicates with the device directly. All communications happen with the device controller. The operating system will give commands to the device controller, and it is the controller which will carry out the actual operation on the device. So now let's see how the operating system perceives these IO devices. So this is the device, and here we have the operating system. And as we know, the operating system will not communicate with the device directly. There will be the device controller that will be sitting between the device and the operating system. Also, within the device controller, there is the interface, that is the device controller interface, which consists of a set of registers with which the operating system communicates. The operating system can read or write these registers to check the status, to give commands. So it is these set of registers with which the operating system interacts. And as you can see, from the perspective of the operating system, the IO device appears as a set of registers because these are the registers with which the operating system interacts. So this is how the hardware interface looks like from the perspective of the operating system. So let's now talk about how the operating system manages the IO devices. So as we know, the operating system has two fundamental responsibilities in the computer system. The first one is to make sure that the hardware is easy to use and that it accomplishes by providing an abstraction which is much more easier to use and is more powerful than the actual physical resource. And the second fundamental duty is to ensure that the hardware is used efficiently and that it ensures by doing a proper resource management. So let us now see how the operating system manages the IO devices and makes it easy to use. So let us start the discussion with this compute stack. As you can see, it has three layers. At the very bottom, there is the computer hardware. Then there is the hardware interface. On top of the hardware interface, there is the operating system. And over the operating system, the user applications are based. So in the hardware layer, we are now concerned with the IO devices. So there are two parts here also. At the very bottom, there is the device itself. And then over the device, there is the device controller that is responsible for managing the device. And there are two interfaces. The first one is the device interface. And the second one is the device controller interface with which the operating system interacts. So now let us take a hypothetical computer system which has these IO devices. As you can see, here I have taken 6 IO devices. The first one is the hard disk. Then we have a USB stick. This is the CD, followed by mouse, keyboard, and display. So as you can see, for every piece of IO device, there is a associated device controller. So there is the disk controller, USB controller, and so on, right? And the thing is, each of these controller, right, is a very specific electronic chip. A device controller can only manage the device that it is associated with. It is designed to do only one particular job. For example, the disk controller can only manage the disk. It cannot manage any other device. That is how it is designed. So what we will do, we will focus on 3 IO devices, the storage devices, the hard disk, USB stick, and the CD-ROM. So we'll see what are the difficulties with using this device controller interface. That is, what is the complexity that is underlying in this interface and how the operating system simplifies this hardware interface. So let's see this with an example. So let us now see what is the challenge with using this device controller interface. So as you can see here, no two device controller have the same interface. All of the device controllers have a very unique interface. So why is this the case? So as I already said, that the device controller is a very specific electronic chip that has been designed to control the device that it is associated with. So the point is that the disk controller can only control the disk. It cannot control the USB stick or the CD-ROM. And the set of registers that are part of the disk controller interface, they will be very specific to how the disk has been designed and implemented. And hence the set of registers in these controller interfaces will all be very different. So this was about the set of registers. It's not just about the set of registers. At a logical level, each storage device exposes the interface to the operating system that it is a sequence of blocks. So as you can see, each of these storage devices, the disk, the USB controller, as well as the CD-ROM, exposes the same interface that it is a sequence of blocks. But as you can see, even here there is a lot of difference. The number of blocks, the block structure, the size of the blocks, each of this is very different, right? So although each storage device exposes the same interface, that is, it is a sequence of blocks where each block has a unique address, the underlying block structure is very different. So now the problem with dealing with these different interfaces is that when you are writing a program as a software developer, for doing the same thing, you will have to write different pieces of logic. So as we know, all of these storage devices have the same purpose, that is to store data persistently. But let's say if you're writing a program to read or write data from these storage devices, then for doing the same thing, you'll have to deal with different interfaces. There will be different sets of registers. As you can see, the block structure is also very different. So for doing the same thing, you'll have to write different pieces of logic. And this is very counterproductive and non-intuitive as a software developer. So you can see what is the underlying complexity with using the device controller interface. So this is what the operating system has to simplify. So let us now see how the operating system simplifies this complexity of the device controller interface. So we said that the complexity lies in the fact that all of these interfaces are different and unique, right? So what the operating system does, that it for similar types of devices. So in this case, these are all storage devices that are used to store data, right, persistently. So for similar types of devices, the operating system defines a single and uniform interface. Now, what happens is that all of these storage devices have to follow this single uniform interface. So there are three different interfaces in this case, but all of this have to finally follow this single uniform interface, right? And at a logical level, we know that the storage devices are a sequence of blocks. So here also the operating system is saying that I expect the storage devices to be a sequence of blocks where the block structure is also uniform. The block sizes should be same. It should not be the case that every device has their own block structure or block size. It should be a uniform block structure, right? So now that the operating system has defined this device neutral, we can say device neutral uniform interface, someone has to bridge the gap between this device specific and device neutral interface. And that someone is the device driver. So basically, just like with every piece of IO device, we had a very specific hardware, that is the device controller. In the same way, with every device, we have a very specific piece of software associated with it, that is called the device driver. So as you can see, with the disk, we have the disk driver. USB, with the USB, we have the USB driver. And similarly for the CD-ROM, we have the CD-ROM driver. And it is very similar to how we had the controllers for each of these devices, right? So now the responsibility of the device driver, the first one, as you can see, what it is doing is that it is bridging the gap between this device specific and this device neutral interface. So if you talk about the disk driver, then all of the logic of dealing with the disk, the peculiarities of how the disk has been implemented, right? Everything will be encapsulated into the disk driver code. So the disk driver is responsible for bridging the gap between this disk interface and the device neutral uniform interface. In the same way, the USB driver will be bridging the gap between this USB controller interface and this uniform interface. So all the logic of how the USB device works and operates will be captured in the USB driver. In the same way, it works for the CD-ROM driver, right? So let us now talk about how the device driver bridges the gap between the device specific interface and the device neutral interface. So now what will happen is that the operating system will give commands at this level, that is the uniform interface, and it will be very device neutral. And now it's the responsibility of the device driver to convert those commands into device specific commands. So let's say the command is to read some blocks. Even if we have to perform the same operation, the exact commands that will be given to the disk will be different from the commands that will be given to a USB stick, right? So the driver has to convert the device neutral commands into device specific commands, right? And not just that, the block structure is also very different. The number of blocks, so they have to map the device neutral blocks into these device specific blocks. So this is how the device drivers will be bridging the gap between the device neutral and device specific interface. So you see how the device drivers make the IO devices very easy to use. Now we as users do not have to deal with the specifics of the device. They have the device drivers have captured the device specific code, right? So device driver is a very central idea, the key idea behind making the IO devices easy to use. So now let us talk about some more points related to the device drivers. So in the previous slides, we saw that the device drivers provide a uniform interface for the IO devices to the user. And there we saw the example of the storage devices. So let us see a demo and see this working in practice. So this is the view of the storage system on my computer. So the C and D drives are part of the internal hard disk, and the E drive is present on the external hard disk. And both of these hard disks are have been manufactured by a different company. But it does not matter. I, as a user, have been provided with the same view of the storage systems. So as you can see, there is a file on the D drive, and that is called hello.txt. It has a message, hello guys. I have the same file on the E drive, and if I open it, you can see there is no difference between the two files. I have been provided with the same view of the files. Does not matter whether they are present on the internal hard disk or the external hard disk. So this is how the device drivers provide a very uniform interface for all the storage devices in the system. And it's not just limited to storage devices. We'll see some examples of other classes of IO devices as well, and see how the device drivers provide a uniform interface for them. So let us see some more examples of how the device drivers provide a uniform interface for other types of IO devices as well. Let's take the example of display. So this is the display settings from my computer, and in my computer there are two displays, one that is part of the laptop, and another is a extended display monitor that I have attached to my system. And as you can see both of the displays have the same interface, right? I, as a user, have been provided with a similar interface for both these devices, even though they have been manufactured by different companies. So I can adjust the brightness for both the displays in the same way. The point is, the user journey for both the displays remains the same. I can adjust the resolution, I can change the orientation. So you see how the operating system has provided me with a uniform interface for both the displays, and this has been made possible by the device drivers. So let me show you some more examples of how the operating system provides us with a uniform interface for the IO devices. Let me give you the example of the audio devices. So again, as you can see in my system, I have two options to receive audio output. The first one is inbuilt into the monitor display, and the other one is part of the laptop. And both of these audio devices are manufactured by different companies. One is from AMD and another is from Realtek. So these audio devices, the controller's interface will be different, but I, as a user, is provided with the same consistent interface for both of these audio devices. I can change the like volume, the left and right channels for the AMD device in the same way that I can do for the Realtek device, right? So even for the audio devices, I am provided with a uniform interface, and this extends to all classes of IO devices. The operating system ensures that the user is provided with a uniform interface. They don't have to go through the differences that are at the device controller interface level, right? So we just saw several examples of how the operating system provides us with a uniform interface for different types of IO devices. We saw the example of storage devices, the displays, and the audio devices. So let us now talk about how the operating system identifies different classes of IO devices, and for each of them it defines a uniform interface. So here you can see we have now, apart from storage devices, we have some other types of devices as well. This is the keyboard and this is the mouse. And basically now the interface, the device driver interface that the operating system has defined for these devices is different from the storage devices. Basically, these are two different types of devices. The storage devices are basically block oriented devices. So the data on these devices are stored as a sequence of blocks. So when we are dealing with storage devices, we have to deal with blocks. So this is the device driver interface that the operating system has defined for block oriented devices, right? And let's talk about these devices, the keyboard and the mouse. So these are character oriented devices. So if you see, the input from the keyboard as well as the mouse comes as a stream of characters, which is very different from the sequence of blocks view that we have for storage devices. So these are character oriented devices, and for these types of devices also, the operating system has defined a different type of interface. So as you can see now, the keyboard controller and the keyboard mouse controller, so not the controller, the drivers. So the keyboard driver and the mouse driver have to bridge the gap between the keyboard controller interface and the mouse controller interface respectively to the character oriented interface that the operating system has defined, right? This is different from the block oriented devices. So now the operating system, what it is doing, it is identifying a few classes of devices. So in this case, we saw two examples, block oriented devices and character oriented devices. And for every class of devices, it has defined a uniform interface, and all of the devices that belong to that particular class, they will have to follow that particular device neutral interface, right? So this is how the operating system is able to provide a uniform interface for different classes of IO devices, right? We just saw several examples. So as you can see, the operating system, the kinds of different classes of devices that exist, I have shown some examples. So first of all, the first class is the block interface. So there are certain devices like the storage devices, which act as a sequence of blocks. So the view that the operating system has for the block interface devices is that they are a sequence of blocks, and each block has a unique address, and the interaction happens in terms of blocks. So this was the first major class of IO devices. Then we have the character interface devices. So these are the devices which send and receive data as a sequence of characters. So here we have examples, that is keyboard, mouse, printer. So these are all the devices where the communication happens as a stream of characters. So they are another class of devices, and these devices are different from the block interface devices. Another very important interface or the class of devices is the socket interface. So all of the devices that are dealing with the network communication, that is sending and receiving packets for the computer, they come under the socket interface. So the socket is an abstraction again, which the operating system defines for network devices, and all communication happens through the socket, right? So if we have to send any data, we send that to a socket, and if we have to receive any data, then we receive that from a socket in the computer system. So both the Wi-Fi adapter as well as the wired adapter, that is the LAN interface, both of them will be classified under the socket interface. So there will be many more such device classes. I have shown some of the examples. So now you understand what the operating system does. It first of all identifies different classes of devices, and so it groups similar devices into one class, and for every device class, it defines a device neutral interface, and all of the devices that are belonging to that particular class will be following that device neutral interface. And that is how the operating system will be providing a uniform interface for similar types of devices. So let us now talk about the device driver interfaces of different operating systems. So here we have two operating systems, one is Windows and the other is Linux. So if you see, again we have the same storage devices and the device controller interface remains the same. However, the device neutral interface that Windows defines for the storage devices or the block oriented devices is very different from what the Linux defines. And this is bound to happen because Windows and Linux are developed by different sets of people, and they can choose how they want to model the block oriented devices. So the point is that this device neutral interface will be different and specific to the operating system. So now as a device manufacturer, if I am making a hard disk, then if I want it to support both on Windows and Linux, I have to write two sets of device drivers. So as you can see, this device neutral interface is different from Windows. So now I have to bridge the gap from the disk interface to two different sets of device driver interface, one for Windows and another for Linux. So you can see for each of these storage devices, there are two drivers, one for Windows and another for Linux. So now it is the responsibility of the device manufacturer to write as many device drivers as the number of operating systems that they want to support. And this is again a challenging job which the device manufacturers have to do. So as you can see, let's say we have two operating systems in the market, the Windows and the Linux, and they have their own device neutral interface. So if I am manufacturing a disk, then I have to write two device drivers to support it on both the operating system. The same is true for all the devices. Now imagine the number of device drivers that are there in the market. Every device manufacturer, even for the same device, there are different companies that are manufacturing those devices, and there are so many operating systems. And for every type of device, every combination of device and operating system, we now require a device driver. So you can understand all of the complexity of device related code has been captured in the device driver, right? So this is how device drivers are supported on devices are supported on different operating systems via the device drivers. So this is how the operating system simplifies the usage of IO devices by providing the device drivers. So these device drivers provide a uniform interface for this wide variety of IO devices, right? And the device drivers basically abstract out the complexity of the IO devices. The device specific part, the code that is related to handling device specific behavior has been captured or encapsulated into the device driver. So this is how the operating system fulfills its first fundamental duty of making the IO devices easy to use by providing the concept of device drivers. So now let us shift our attention to the second responsibility of the operating system. Let us now see how the operating system manages the IO devices and make sure that they are used in an efficient manner. So if you see this compute stack, there are several user applications in the computer system, and all of them require these set of IO devices, right? So these IO devices are a shared resource and needed by all the user applications. So let's talk about a few examples. So the storage, right? The storage will be required by all the user applications for storing the files. Every user application wants to use the display for displaying whatever output they have produced, right? The peripherals, including the keyboard and the mouse, the user will be using these peripherals to give inputs to all the user applications, right? And finally, if you talk about the network, then if it is a networking application, then it wants a share of the network also, because it has to send or receive data packets. So all in all, the set of IO devices are a shared resource, and the operating system has to carefully allocate these resources to the different user applications so that each of them can interact with the user. So let us now see what else does the operating system do apart from resource allocation in the context of managing the IO devices. So we'll first see how an IO device operation works. So let's take an example. Here you can see there is a process which, let's say, want to read some data from the IO device, that is the disk. So it will initiate a read operation, and the operating system will come into the picture. It will invoke the device driver, and it is the device driver which will operate the device. It will read the data from the disk. And as you can see, it will take some time to read the data from the disk. And in the meanwhile, when the data is not there, the process cannot continue execution because it requires the data for further processing. So it will be kind of blocked. You can say it will be waiting for the data to arrive. And as you can see, it is continuously polling, or you can say checking whether the data is available or not. So it checks the data, it checks for the data, it sees that it is not available, and it continuously polls after a periodic interval. And finally, when the data is available, this polling is successful, and then the process can continue its execution, right? So this period that you see, the gray region, this is like a wastage cycles. Here the process is doing nothing but just checking whether the data is available or not. And the thing is, IO devices are slow. It will take a lot of time to read the data from the device. If we compare the time that it takes to complete an IO operation with the speed of the CPU, then the CPU is very fast. It can execute millions and billions of instructions per second. But IO devices are slow. They operate at the speed of the human user. So here the disk operation, reading or writing from the disk, can take some time. And it's not just the disk, any peripheral device, for example, the keyboard or the mouse. These are devices which operate at the speed of the human, and it can take some a few seconds to for an IO operation to complete. And within that time frame, the CPU can do a lot of work. But as you can see here, it is just polling whether the IO operation was completed or not. So these cycles that were wasted in just checking whether the operation was complete or not, this can be utilized for doing something better. So let's see now what the operating system does to solve this problem of wasted time cycles. So let us now see how the operating system ensures that this time that you see here, which is being wasted in just polling the IO device, is used to do something more useful. Let's see what the operating system does. So this polling based IO is replaced by something called as interrupt driven IO. So now what the operating system does, whenever a process initiates an IO operation, it knows that it will take some time, and instead of having the process A, in this case, just polling the IO device, it pauses that process A and switches to some other process, that is process B. In the meantime, when the device driver is operating the device and reading the data from the device, In that time, the CPU can do some useful work, some meaningful work. Here, process B is executing. And when this operation completes, then it can initiate an interrupt. So an interrupt is like a notification to the operating system that, okay, the operation has complete. So once the operation is completed, then the operating system will pause process B and then resume process A, because now the data that it was requesting is available. So this notification system, that is the interrupts, is implemented by the operating system. And now, as you can see, with this concept of interrupts, both the CPU and the IO operation can proceed in parallel, and this leads to a more efficient use of resources. And this interrupt system is implemented by the operating system. So this is how it makes sure that the resources in the system are used in an efficient manner. So this concept of interrupts that we just saw is very important in the context of operating system. We'll spend some time understanding interrupts in the future videos also, but this concept of interrupts is something that we come across our daily lives also. So let us take some examples of electronic devices that we use in our homes. So if you see the washing machine, let's see how you use the machine. You put your clothes in the machine, you start the machine, and then you go on to do some other work. And when the washing of clothes is complete, then the washing machine notifies you or interrupts you in some way. It could be a beep or some sound that notifies you, okay, that the operation has complete. And then you come to the machine and take your clothes. So you see, you don't stand near the machine and periodically check whether the washing has completed or not. You go on to do some other work. You know that when the operation will be completed, the machine will automatically notify you. So this is the concept of interrupts in our daily lives also. You saw the example of washing machine. And the microwave oven, another electronic device, works in the same way. You put your food, and when the food is cooked, the microwave oven will notify you or interrupt you. You don't have to stand near the oven and continuously check whether the food was cooked or not. So you see how this concept of interrupts is not new, and we come across these interrupts in our daily lives also. And the operating system also uses this concept of interrupts heavily, and we will revisit this concept in the later videos. So we have talked in brief how the operating system fulfills its second fundamental responsibility in the context of managing the IO devices, that is ensuring that they are used in an efficient manner. We talked about how the IO devices are a shared resource and they have to be properly allocated to all the user applications. Then we talked about the interrupt driven IO, that IO devices are slow in nature, and this concept of interrupts is very crucial to ensure that the devices are used in an efficient manner. So guys, this was it for this video. In this video, we studied how the operating system manages the IO devices. It makes them easy to use by providing the concept of device drivers, which abstract the complexity of the IO devices by providing a uniform interface. And then we also spent some time understanding what the operating system does in the context of IO devices to ensure that they are used efficiently. So this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.